All right. Chapter 4 is applications of differentiation. Took me a minute to remember where I was. Applications of differentiation. Actually, most of chapter 4 is applications of differentiation in regard to graphing. How you use the derivative to tell different things about the graph of a function. 4.7, we're going to hit another section of word problems. The two big sections of word problems in Calculus 1 are related rates, which y'all seem to have done very well with, didn't have a lot of questions, and then optimization. That's another big use of calculus, finding out what maximizes something or what minimizes something. But 4.1 to 4.6 are just applications in regards to graphs, and we have some new terminology. So this is page 202 in your book, in case you have trouble seeing what's on the screen. I really just need to read a little bit to you, or read a little bit with you. Good morning. All right, in calculus, much effort is devoted to determining the behavior of a function on an interval I. Does the function have a maximum on the interval? Does it have a minimum value on the interval? Where is the function increasing? Where is it decreasing? Those are some of the questions that we're going to be answering in chapter 4. First blue box, definition of extrema. Let f be defined on an interval I containing some x value c. Then f of c is the minimum value of the function on the interval I if f of c is less than or equal to f of x for all x in the interval. In other words, f of c is the minimum on the interval as long as it has c has the lowest y value on that interval. And f of c is the maximum value on the interval as long as c gives you the highest y value on that interval. The minimum and maximum value of a function are called the extreme values, or extrema. The minimum and maximum value of a function on an interval are also called the absolute minimum or absolute maximum or global minimum or global maximum. I just think they added the global this edition. I don't think it said global before this edition. But when you have a closed interval, then there's going to be an absolute highest y value and an absolute lowest y value. That is to be compared to, or to not be confused with, a relative minimum and a relative maximum, which we'll talk about in, I think maybe we get to it here. But absolute extrema are guaranteed on a closed interval. This example A illustration shows you an interval from -1 to +2. Now remember, when you have brackets on an interval, that means including the endpoints, and that's what makes it a closed interval. If you had parentheses on the -1 and the 2, that would mean an open interval, and we'll talk about that as well. You can also have a half open interval with a bracket on one end and a parenthesis on the other. But in this example A, you have a minimum value which occurs right here, and a maximum value which occurs here at one of the endpoints on that interval. And then in the B part, you have an illustration of a graph that is an open interval, graphed on an open interval, not including the endpoints. You can't say that there's a maximum value there if the function's not defined there. Really, you can't say that there is a maximum value on that interval because I can get infinitely close to 5. I just can't get to 5. So there's no maximum value on the open interval. You tell me what you think is the maximum value, I can tell you something that's closer to 5. If you tell me you think the maximum value is 4.99, I can tell you, no, I can get bigger than that, 4.999. So there's no maximum value, but there is still a minimum value at 0, 1. And then the third illustration shows you an interval over which the graph has a maximum value, but it doesn't have a minimum value because the function's not defined at what looks like it would be the lowest point on that graph. It looks like the lowest value on the graph might be 1, but the graph doesn't actually get to 1. It just gets infinitely close to 1, so there's no minimum value. Theorem 4.1 says if f of x is continuous on a closed interval from a to b, then f has both a minimum and a maximum value on the interval. Now, b and c didn't have a maximum or a minimum value. Well, b didn't have a maximum value, c didn't have a minimum value, but the function wasn't continuous on a closed interval. In the b part, the endpoints weren't included, which means it wasn't a closed interval. And in the c part, the graph wasn't continuous everywhere on the interval, and that's why those two were not guaranteed to have a maximum or minimum value. But if you have a function that is continuous on a closed interval, then it's going to have an absolute highest point and an absolute lowest point. Next page. This graph in figure 4.2 has a relative minimum at the point, in figure 4.2, the graph has a relative maximum at the point 0, 0. Relative maximum just means not necessarily the highest point on the entire graph, but higher than what's around it. If that is x cubed minus 3x squared, there is no absolute highest point on the whole graph, because we know that goes forever down on the left and forever up on the right. So there's no absolute maximum for that function. But we would say 0, 0 is a relative maximum because it's higher than what's on either side of it, and 2, negative 4 is a relative minimum because it's lower than what's on either side of it. And the box there, relative extrema, is the technically correct and yet hard to read definition of relative extrema. Previous box was absolute extrema, absolute highest value on an interval, or absolute lowest value on an interval. This is just relative max and relative min. All right, one other thing. Actually, save that one other thing for a minute. Look at the homework with me. Page 207. The first 6 problems say find the value of the derivative if it exists at each indicated extrema. And number 2, we have the graph of cosine pi x over 2. It looks just like the graph of cosine x, except for its period has been changed because of that coefficient of x. And we're asked to find the value of the derivative at 0, 1, and at 2, negative 1. We could find the derivative. We absolutely could. And then we could put 0 into the derivative, and that would give us the slope of the tangent line right here. We could put 2 into the derivative, and it would give us the slope of the tangent line right here. Do we really need to find the derivative in order to find those 2 slopes of the tangent line, or can you see what the slope of the tangent line would have to be right there? Yeah, you can see it. It has to be 0. The tangent line would be horizontal both at that point and that point, so the slope of the tangent line, or the value of the derivative, would be 0 there. What about here at the point, at that point? I don't even want to read. What's the slope of the tangent line there? 0, because the tangent line would be horizontal. Number 6, what is the value of the derivative at the point 0, 4? What do you know about where derivatives do not exist? Where do derivatives not exist? At sharp turning points. And there's a sharp turning point at 0, 4. I could find that derivative of the absolute value function. I'd have to use the 2 pieces of the absolute value function. One part of it for x is less than 0, and one part of it for x is greater than 0. And we'll do an example like that. But if you remember that the derivative doesn't exist at sharp turning points, then you don't have to do any of that work on number 6. You could just say the derivative is undefined at 6, or at 0, 4. Yes, sir.
On number 4, what negative 1, 0, would that be undefined?
Oh, I didn't even notice that it was labeled. The point negative 1, 0. Trying to see if I can give you a hint or if I need to tell you. You remember that when you write the limit as x goes to something, something, you're talking about the two-sided limit, and in order for the two-sided limit to exist, both one-sided limits have to exist, and then we talked about the same thing being true for derivatives. We very rarely use the term two-sided derivative, but technically the two-sided derivative means both one-sided derivatives exist, and so you're absolutely right. The derivative doesn't exist here because you can't differentiate that function coming from the left. So yes, it will be undefined right there as well. All right, so just looking at 1 through 6, or the 3 even problems we talked about, what does it seem like what does it seem like you could say about the value of the derivative at the high points and the low points of the graph? It's 0 here, it's 0 here. What about number 6? At its high point, the derivative wasn't 0. It doesn't exist. All of the 3 examples that we looked at, where there were high points or low points, the derivative was either 0 or it didn't exist. Now, we're not going to prove that's true. I'm going to show you the theorem that says that's true, and somebody else has proven that theorem. But if you want to prove it yourself, then get a master's in math, and you will. All right. That thing that I wanted to go back to on page 204. In the examples that we just looked at, the derivative is either 0 or does not exist at each relative extrema. Those x values at those special points are called critical numbers. And here's the definition of a critical number. Something very important you need to understand about that definition. Let f be defined at c if f prime of c is 0, or if f is not differentiable at c. If the derivative is undefined at c, then c is a critical number of the function. All right? The shortcut and wrong way to remember that is wherever the derivative is 0 or undefined, that's a critical number. What important thing did I just leave out of that box? I said the function has to be defined at c. So if you have a value which makes the derivative 0, but the function's not defined there, it can't be a critical point. You can't have a critical point where the function's not even defined. So in order to be a critical number, yes, the derivative has to be 0 or undefined, but on top of that, the function itself has to be defined at that point or it can't be a critical number. All right, the next examples on page 207. Say find the critical numbers. And for example, number 12, we start off with a nice polynomial function. If I'm looking for critical numbers, then I'm aware that it has to be a number for which the function is defined, or a number in the domain of the function. What's the domain of this function? You can put any number in the whole wide world into a polynomial function. Won't blow it up. So the domain is negative infinity to infinity. I don't have to worry about that part of the definition of a critical number because there's nothing that makes the function itself undefined. How do I find those numbers that make the derivative either 0 or undefined? Well, first I need to find the derivative and then set it equal to 0. Is there anything that makes that derivative undefined? No, it's a polynomial as well, so nothing makes it undefined, but we can find what makes it 0 by factoring. What are the critical numbers for that function?
0, 2, and 8.
Yep. It doesn't matter in what order you write them. I tend to write my critical numbers left to right because when I finally get to 4.6 and start graphing using this information, I graph from left to right. All right, that's all we have to do on those. Number 14. Go for it. Find the critical numbers for that function. Tell me first, what's the domain of that function? Yeah, there's nothing that I can get 0 in the denominator by squaring an x and adding 1. No real number makes that denominator 0. So the domain is -infinity to infinity. Now find the critical numbers. Is that what you got for the derivative, factored completely as possible? You can kind of see why it's always been a goal of ours to write the derivative as factored as completely as possible. It's easy to look at it in that form and find the critical numbers. What are they? Before I write that down, let me double check. Is the function defined at -1 and +1? Yeah. So as long as the function is defined, anything that makes the derivative equal 0 or undefined is a critical number. We need to do something that's not so pretty and algebraic. But what about 16? I think it's always good to start by writing the domain for the function. because then you'll remember what cannot be a critical number. If it's not part of the domain, it can't be a critical number. So what makes that function undefined? What do both of those trig functions have in the denominator? If you write them in terms of, they both have cosine in the denominator, and what makes cosine undefined? Or not makes cosine undefined, but if you have cosine in the denominator, what can not be, well, that sentence is coming out weird. If you have cosine theta in the denominator, what can you not let theta be? It's at the half pi's. Pi over 2 and 3/2 pi would make cosine 0. And if you have cosine in the denominator, that's what you can't allow to happen. So the domain, I'm going to say theta can be anything but pi over 2 and 3/2 pi. So no matter what else, those cannot be critical numbers. All right, go for it. So far, so good? You got the derivative. Wasn't hard to write it, factored as completely as possible. It's not hard to set each factor equal to 0. It's not hard to solve that first equation. What makes secant equal 0? What does the graph of secant look like? Show me with your hands. There's this concave U part and this concave up part and this concave down part. Where do those start? What's that? And what's the vertex of this one and the vertex of that one?
0,
1. I think it's -1 and +1. It goes like this and this and this and this, and it turns around at +1 and -1. Secant and cosecant don't have any x-intercepts. So what makes them 0? Nothing. There's nothing that makes that 0 because it doesn't have any x-intercepts. There's stuff that makes it undefined, but we've already eliminated those from the realm of possibility. We've already said secant can't be 0, or cosine can't be 0. So nothing is going to make that 0 or undefined. What about this? How can we solve that? But then I would have to solve it by squinting. I would have to squint hard enough to see values of theta whose tangent would be half the opposite of the secant of theta at that point. I got enough wrinkles on my forehead without that. All right, that would absolutely work, but then I don't think I could solve it. Any other ideas? William, what do you think it is?
When you had the 2 secant tangent plus secant squared theta, you could actually take out a secant squared, and that would.
Hold on, let me check out that. You're saying take a secant squared out of that?
Yes.
That's because you're doing stuff in your head that I can't do in my head, William. I look at that and I don't think, oh, I can factor a secant squared out of that, because this guy only has a secant to the first. So give us some middle steps if you're going to do that, William.
Turn the tangent into a sine times secant, so then you have 2 secants in the first term and 2 in the second term.
It kills me when he does that on his test. Like, what the heck have you done, William? That would work. That would work, and I'm starting to think like you. I think that actually makes me better.
It actually makes finding the second one easier.
Yes.
Because you don't have the tangent and the secant, you only have the sine.
Yes, you can absolutely do that. If you didn't happen to think of that up here, you can still get here and write things in terms of sine and cosine. But at some point, I have to realize I don't think I can solve that equation with 2 trig functions in it. So if I write it, let's see if that would still work here, William, or if I need to back up. If I wrote that as sine over cosine and that is 1 over cosine, I think I can still do it right there. We could look for what makes that either 0 or undefined. I'm going to say or undefined right there. But we've already said the original equation's not defined anywhere. Cosine is 0, so those can't be critical numbers. The only critical numbers are going to be what makes that 0, and what makes a fraction 0 is whatever makes the numerator 0. Speaking of which, it made me sad that, which problem was it on the retest? Number 16. On the retest, number 16, it said find where the tangent line is horizontal. And several folks got the derivative, but didn't know how to find what makes that fraction equal 0, which made me really, really sad. Because what makes a fraction 0? Whatever makes the numerator 0, and what makes that numerator 0? 0. So 0 was the value of x that made that derivative, or that tangent line, horizontal on the retest. All right, so, yes, sir.
So if I wrote x equals 0, would that be right?
Let me see what the problem said. Did you write that and I didn't see it, Cooper?
Yeah, you just put minus 4.
Oh. Yeah, give me that and let me look at it again. Y'all always look over your tests. Thank you, sir. Oh, that's on number 15.
Oh.
Yeah, 16 doesn't have a mark on it. That's 15.
Okay.
My marks are just slanted.
Oh, okay.
All right.
There's minus 4 besides 16.
It's coming from number 15, though.
There's a minus 6 besides that.
That's where the line is. That's,
Oh.
that's okay. I forgive you. All right, so now we finally, William may have thought to make his substitution up here. I may not have thought, hey, I'm going to have to do some kind of substitution until I got here. But at the point where I'm trying to solve an equation that has 2 trig functions in it, I need to figure out a way to write one in terms of the other, or both in terms of some single function like sine or cosine. So we're just looking for what makes sine negative a half. And so our critical numbers are 7/6 pi and 11/6 pi. On the unit circle, that's right below the negative x-axis, or right below the positive x-axis, square sine is negative a half. There we go. All right. Let's just do one more of those so we can get to our other set of directions. Number 18, g of x equals 4x squared times 3 to the x. On the retest, it made me really sad if I gave you 2 chances to memorize the derivative of a to the ugly, and you still didn't have it memorized. Or you might have had it memorized the moment before you walked in the room. But you should have written it at the top of your paper as soon as I gave you blank paper. All right, find that derivative. Hey, tell me first, what are the, what's the domain of that function? What can I let x be? I can square anything in the whole wide world. I can raise 3 to any power. So I'm not going to have to worry about excluding anything from the domain or from the critical numbers. All right, now find the derivative in the critical numbers.
It's just supposed to be 8x.
Yeah, I was double checking right then. I was about to find that. First derivative of the second plus the second times the derivative of the first. I can factor out. So what you have for the derivative, factor it as completely as possible. Is there anything that makes 3 to the x either 0 or undefined? Nope. What about 4x? 0. 0 is a critical number. What about that other guy? Can you solve that? Tell me first if there's anything that makes it undefined. Well, I can take any number in the whole wide world, multiply it by natural log of 3 and add 2. So nothing makes it undefined, but what about what makes it 0? How do I go about solving that ugly equation? Tell me what you're thinking, Sam.
Subtract 2 and then divide by natural log of 3.
Yeah. And if you want an exact answer, that's all I can do. If you want a decimal approximation because you're going to graph this thing, then punch it on the calculator. But as far as exact answers go, the 2 critical numbers are 0 and negative 2 over natural log of 3. All right. There's 2 other things I want to show you in the book. Theorem 4.2. We talked about at the top of the page the definition of a critical number, and then theorem 4.2 is kind of what we discovered on our own. If f has a relative minimum or a relative maximum at x equals some constant, then that constant has to be a critical number. if there's a relative max or min, it can only occur at a critical number. It can occur somewhere the function's not even defined, right? But it can occur at something that makes the derivative 0 or makes the derivative undefined, as long as that doesn't make the original function undefined. Is it true that, I forget whether to call this the inverse, converse, or contrapositive? I forgot my logic terminology here, but is that true if you read it backwards? If C is a critical number, then F has a relative max or min there? I remember the word for that. I should know. It's either inverse, converse, or contrapositive. I just can't remember which one of the three it is. I think it's converse. Would it be true that if there's a critical number, then it has to be a relative max or min? No. Just because this is true doesn't mean it's inverse, converse. I think contrapositive is always true, but I'm getting kind of off on a tangent there. Nothing to do with trig. So it's not true that if C is a critical number, then it has to be a relative max or min. It's just true if there's a relative max or min at C, then C has to be a critical number. All right, and the last thing.
Can you show some example of why that wouldn't be true?
Yes, absolutely. There was actually, let's see. We're talking about somewhere there's a critical number that's not a max or min. I'm sure there's probably an example. A critical number that's not a max or min. If, for example, no, that wouldn't work. If this, yes, I found one. This figure 4.1, the C part, that 1 would be a critical number because the function is defined there, but the derivative's not defined there because the function's not defined to be the same thing as the value of the derivative. All right, so that was a great question, and I was afraid I wouldn't be able to come up with it off the top of my head, but this function is defined at 0, but it's not defined to be the same thing as the rest of the function. So the function is defined, but the derivative is not defined. That makes 0 a critical number, but it can't be a minimum. Okay. All right, so the last thing I want to show you in the book is these guidelines for finding extrema on a closed interval. If you have a closed interval, there is going to be an absolute max and an absolute min. It may occur at a critical number, or it may occur at one of the endpoints. So all this box is saying is to find the extreme values, the absolute extreme values on a closed interval, you need to find the critical numbers. You need to evaluate the critical numbers to find their function values, but also evaluate the function at its endpoints. I just make a little XY chart, put my critical numbers and my endpoints on that XY chart. Get the Y values from the original function. The highest Y value is the absolute max. The lowest Y value is the absolute min. All right, so we're not going to have time to do a whole bunch of these. But let's see, we'll do something that is a polynomial and something that's not, because we have about 7 minutes. Number 26. These say find the absolute extrema. And what we have to keep in mind is that absolute extrema on a closed interval, And then number 26, the closed interval that we're given is from 0 to 3. The absolute extrema on that closed interval can only occur at the critical numbers or at the endpoints. So I'm going to find the critical numbers, and then I'm going to put those critical numbers and those endpoints on an XY chart, find the highest Y value and the lowest Y value. So the derivative is 8x squared minus 6.
I think the derivative of 2x cubed would be 6x squared.
I think you're right. And I think that would be easier to solve. I cubed the 2 instead of multiplied 3 times the 2. Thank you. That slipped past me. 6x squared minus 6. So I can factor out a 6. And I get my critical numbers are plus or minus 1. So my absolute extrema can occur at -1 or 0 or +1 or 3. I just like to put my x's in order from lowest to highest because that's what I'm going to do when I graph. But let me just tell you, I think I've got all those y values. And if I do, wait, number 26, 0, 0, 1, -4. Hey, this is why I wanted to do this example. Could -1 possibly be an extrema on the closed interval that we're given? No, why not? It's not even in the interval that we're given. So I didn't really need to put that on my XY chart. I should have said -1 is not in the interval that we're given. And so I don't even need that there. When I ask you for extreme values, I'm asking you for y values, the function values. So what's the absolute minimum? -4 and the absolute maximum? 36. 1 and 3 are where they occur, but absolute extrema are always y values. So the absolute min is at -4, and the absolute max is 36 on that closed interval. But I know if I looked at the function over its entire domain, it wouldn't have a max and a min, because x cubed goes down on the left, up on the right. There's no absolute highest and lowest value for that entire function, but on that closed interval there are. All right, 26. I told you we'd do something with absolute value in it. Number 32, absolute value of x plus 4 on the interval from -7 to 1. Is there anything that makes that function undefined? No? So I don't have to worry about that. When I go to find my critical numbers, I don't have to think about what makes the function undefined because the domain's -infinity to infinity. What does that graph look like? The V shape that turns around where? At -4. Anything more than -4, you're going to get out that number plus 4. But anything less than -4, you're going to add 4 and then get out the opposite of that because you're going to take the absolute value. As long as you can look at it and say the V turns around at -4, then that's your critical number without actually having to find the derivative.
What about the greatest integer function, like number 30.
I'm going to try to squeeze that one in too. So sometimes find the derivative. Sometimes just think about the graph and think that graph is not differentiable at -4 because one derivative would be +1, the other derivative would be -1. And so that makes -4 a critical number. Let me just say when I put the endpoints and the critical number and an XY chart, I got these values. So what's the absolute min?
0.
And the absolute max? Yeah. And then the next ugly thing I saw there was the absolute or the greatest integer function. What's the domain of that function? Anything. You could take any number, subtract it from 2, and then apply the greatest integer function to that. So we don't have to worry about anything that makes the function undefined. If the only way I could find that derivative would be to use the definition of the derivative. I know by looking at the graph that it's not continuous at any integer. It's the step function, so it's discontinuous at every integer. That makes every integer a critical number, but how many integers are there between -2 and 2 inclusive? -2, -1, 0, 1, and 2. Because I know what the graph looks like, because I graphed it last night, I know that its highest point is going to be at the left endpoint, and its lowest point is going to be at the right endpoint. And again, that was not doing any calculus. That's just what I know the graph of the greatest integer function looks like. So when I made an XY chart for that, I didn't bother putting in those 4 middle integers. I just found the Y values for the endpoints. My max was 4 and my min was 0. As you do these, if you'll just keep in mind that absolute value on a closed interval, absolute extrema on a closed interval can't be a number that's not even on the interval and can't be a number that's not in the domain of the function. Alrighty, see ya. I'm sorry, what? Our homework, it is on the assignment sheet, but where do I have it written down? I have it written wherever that, yeah, 1 through 43 odd. Yep, right there. If I take it tomorrow, I'm probably not going to take it Wednesday, but any other time, yeah, you can definitely do that anytime. Yeah.
Do something with critical numbers and pre-count.
I started calling them critical numbers where the graph does something special is all that I really said about them. We're going to call that, what I say is, we're going to call these critical, and in calculus, we're going to find out why they're critical. So yeah, I used the terminology. We just didn't really go into it.
I forgot that she did that.
Hey, how are you? Good. I didn't, because we had about 5 or 6 SMHS folks out, but I'm going to take it tomorrow. And SMHS asked me to give progress reports to their kids, something to take home to mama. So I made one for everybody, even one whose mama no longer has to sign papers. There you go. You're welcome. Howdy, howdy. Ah, where was that? Goodness gracious, booby trap. How are you feeling? Still not? I'm sorry.